So what I'm going to go through in this video is how to approach drawing the molecular orbital diagram for a homonuclear diatomic, and so in this case that what we're going to be looking at is N2. Right, so dinitrogen, so if we were to draw out the Lewis structure for this, we have nitrogen triple bonded to another nitrogen with two lone pairs on each one of those nitrogen sides. So the way that you approach any type of MO diagram is that you'll put, the different atoms on opposite sides of your page. So in my case, right, I'm going to have a nitrogen right here, and then I'll have a nitrogen over here, and then in the middle is where you're going to then draw the actual MO diagram, right? That's going to be right there. So that's going to be N2 in this case. So the first thing that you want to do is you want to first draw out for each one of the atoms the atomic orbital energy diagram, and you really only need to do the valence shells, right? So in the case of nitrogen, we can completely disregard the 1s orbitals, right? We're only going to focus on the 2s and the 2p. So in this case, we're going to draw out, right, we have our 2s is going to be down here, and then up here, roughly, right, we'll say our 2p. And so since this, both of them are nitrogens, we should expect the atomic orbital energies to be exactly the same on both sides. So they should be at the same exact spots here, right? So we have those, so 2s and 2p, and then we just fill in with the number of electrons that we have. And so, in the case of nitrogen, we have 5 in the valence shells, so there's going to be 2 in the 2s, and then 3 unpaired ones in the 2p. Now, the first thing that we're going to do is combine together the two 2s orbitals. So in those cases, right, s orbitals only form sigma bonds, and so we're going to have a sigma bonding orbital, and that's going to be lower in energy than our starting 2s orbitals. And then we're also going to have the sigma antibonding orbital, right, and that's going to be then higher in energy than the starting 2s orbitals that we have. So that'll be right here, right, so that's sigma star, right? Sigma star is the same thing as sigma antibonding. So, right, I always like to draw, just to keep track of everything, little lines that connect everything in these cases. Right? So there. So we have everything that we have set up for the 2s. Now, for the 2p, right, there's 3 different combinations that happens, right? You can have, if we draw out what the different orbitals look like, right? So for the 2s, right, the orbitals are just simply the sigma bonding orbitals. So those look like those right there. In the case of the 2p, right, you're going to have your 2pz, you're going to have your 2px, and then you're going to have your 2py that exists. Same thing over here, right, you're going to have 2pz, 2px, and then 2py, right? And so looking at that right there, right, the two 2pz's are going to be oriented towards each other, so those are going to be forming a sigma bond. And then the px and the py's, right, those are going to be then forming our 2pi bonds in these cases right here. Now, one important thing to note is that for essentially when you're looking at the periodic table, right, and if you were to look at the trends of how the MO diagrams look like, there's actually a change in terms of what the ordering is when you go from dinitrogen to dioxygen. In the case of dinitrogen, what happens is that you have actually, after the sigma star here, what you end up with are the 2pi orbitals in this case right here. Right, so you're going to end up the ones that have the combination of, the px and the py together in that case. And then after that is where you get your sigma bonding orbital in this instance. So those combine there. Right? And then the next thing after that, though, is that we're going to then now have the 2pi orbitals that are antibonding, right? The 2pi star orbitals are going to be next. And then all the way up top, we would end up with the sigma star. Now, the reasoning is probably outside of the scope of whatever class you're in for the most part, but it actually has to do with the fact that the energies of the atomic orbitals are actually so close together that you're also getting, combinations of bonding and anti-bonding orbitals between the pz and the s orbitals in those cases, right? But you don't have to worry about that for the most part. If you can kind of just remember that everything, right, from lithium to nitrogen follows this trend right here, where you go sigma, sigma star, pi, sigma, pi star, sigma star, right? You should be in good shape. And then everything after that, right, the oxygen, the fluorine, right, and then, hypothetically, right, neon, would follow then a different ordering, right? And I'll talk about that in a different video. Right, but this right here is like our framework, right? This is the energy levels that we would have in this case. So now all we have to do is start taking all of the electrons that we have for the different individual atoms, and we just start filling it in. So if we go through and we look at the nitrogen on the left side, right, we have a total of 5 electrons. And over here, for this other nitrogen, right, we have 5 electrons as well. So that means that for dinitrogen, right, we should have a total of 10 electrons that we're going to be filling in. So if we go ahead and do that, right, we just start filling them in, following the Aufbau principle, Hund's rule, right, and the Pauli exclusion principle. So we have, 2 that are going to fill into the sigma bonding orbital. We'll have then 2 more that go into the sigma star, right? Next we'll go into the pi, so we'll have 1 here, and then, right, we're at 6 now, and then, 7, 8, right? So now both of those pi bonding orbitals are filled, and then finally, right, we go to the sigma bonding orbital here, right, and then we're 9, 10, right? So now all 10 electrons that we have for our binding combination are all right here. And that's essentially, right, how you draw the MO diagram, right? So we're finished now. All the electrons are in there. We have everything ordered. Everything is set up. If you were going to go a step further, right, and calculate out the the bond order, all you have to do is just simply add up all the electrons that reside in bonding orbitals, right? So in this case right here, that's a total of 8, right? We have 2 right here, 4 right here, and 2 right here, right? Adding that all up comes out to 8, right? So we have the bond order is equal to 8, and then we subtract out all of the anti-bonding electrons, so we only have 2 in this case, right? There's only 2 in the sigma star orbital right there, so we have -2, and divide that whole thing by 2, right? So what we get is 6 divided by 2, which comes out to 3, right? Which tells us that we should have a bond order of 3, which makes sense based off of what our Lewis structure is, where we have the triple bond between the 2 nitrogen atoms. So that's how you approach drawing the molecular orbital diagram for a homonuclear diatomic, in this specific case dinitrogen.